Hello, so this is the video on the generator effect. I was going to upload this last week, but I did one and I just wasn't happy with the quality. So I've gone back to the drawing board and I'm going to break it down into two parts, and hopefully they're quite short and they give you everything you need to know. But if there's anything missing or anything you want in more detail, just let me know in lessons. Right, so I'll put at the top generator effect, and you just need to remember these three things for me. So if you cut magnetic field lines, so you move a wire, a conductor or a coil through a magnetic field, you're going to induce a potential difference. So you need to say that it's a potential difference that you're inducing, otherwise you'll lose some marks. And then the third part is if you have a complete circuit, that conductor, coil, wire that you're moving through the field lines, if it's a complete circuit, then a current will flow. All right, so I'm going to come back to this in a minute at the end, but I'll just draw a little diagram here. So we've got a north and a south, and you can imagine my field lines are pointing from north to south. So if I was to take a wire and I was to move it upward through this magnetic field line, you can imagine that it's moving through those field lines, it's cutting those field lines. So if it ended up here, if this was your wire, what's going to happen is you're going to induce a potential difference. So what that means is one end will be positive, one end will be negative. If that was part of a complete circuit, that would obviously cause a current to flow. Now, if I was to take the same wire and the same magnetic field, but I was to now move it down, so I've reversed the direction that I'm cutting those field lines, F there just for force, what that would do is reverse the direction of the induced potential difference. And if it was part of a complete circuit, that would reverse the direction of the current that flows. So let's rub this out. So if we change the direction that we're cutting the field lines, that's going to reverse the induced potential difference in the current that flows. But we need to also know how we can increase the potential difference that we're going to induce. So the two things you can do are move the coil or the wire or the conductor faster. Because if you move it faster, what you're going to do is cut more field lines per second. And if you cut more field lines per second, you're going to induce a larger potential difference. And then a larger current will flow if it's part of a complete circuit. What you can also do is increase your magnetic field, B field. Because if you increase your magnetic field strength, your magnetic flux density, you go from this sort of situation. So if I just draw three lines to represent the strength of that field, if I was to get a stronger magnet, I'd have lots more field lines. Can't draw all the little arrows, but you can see that per second, you would be cutting more field lines. So if you're cutting more field lines per second, you will get a larger potential difference. Now, the last thing I wanted to do, second to last thing, if I had a field like this, and my field lines were there, let's say I had a wire that was right in the middle, and I moved it horizontally, so my force horizontally, and that could be left or right, you can see that it's not going to cut any field lines, it's just going to move across without interfering with those field lines. When that happens, you do not induce a potential difference. Now that's going to become important in the second video that I do on the dynamo and the alternator. Okay, so last bit then, we're pretty clear on these parts now hopefully. So you cut magnetic field lines, that induces a potential difference, and then in a complete circuit a current flows. Now, this links back to our motor effect because now we've got a current. So current, that itself will induces a B field, a magnetic field around your wire. So remember the right hand corkscrew rule? So if that's the direction of the current, my fingers show the direction of that magnetic field. So now you've got this induced field around the wire within the permanent magnetic field. Remember, we've got this permanent magnetic field with our field lines, and we've got our wire moving up through it. So we're inducing that potential difference, a current's flowing, and this wire will have an induced field around it. So what that means is, the same as the motor effect, the induced and permanent fields interact. Now what that means is there's going to be a force exerted, and the force is always exerted to try to stop the motion of the wire that's causing this. So if I had my north and my south, and I was moving this wire up, then the magnetic field that's induced around this wire is going to cause a force down. So actually, we better just make sure, sorry, I've gone off the table a little bit, but that's meant to be a complete circuit. So when it's a complete circuit and the current's flowing, this force will act in the opposite direction. So you'll find it harder to move the wire up. Now, if I was to break this connection, the circuit is incomplete, you're not going to get this current. If you don't get the current, you don't get the induced field, you don't get this interaction, and you don't get this force. So often questions will say, why is it easier to turn once the circuit is disconnected or broken? It's because the current's not flowing, and therefore you're not getting this magnetic field, you're not getting this interaction, and you're not getting this force against it. Okay, next video will be on dynamo and alternator.